Hello kids, welcome to Unit 4 of IGCSE 0625. Today we will be discussing three topics, which are moment of a force, the line of action of forces, and center of mass and center of gravity. Why we need to understand this is because that whenever we apply forces, in this previous unit, Unit 3, we were discussing only linear forces or forces in one direction that led to only linear motion of the object, right? For example, if we considered forces, we were discussing forces and just one dimension of the motion of the object, right? So in the turning effect of forces, we'll discuss how forces can turn objects around. So let's get into this. So what is moment? We all know moment from our old topic. If you remember that there was, let's say, if there was a small stone and we put a long bar over here, and we can lift a heavier object by using, this long arm, right? And we apply force over here, and we are able to lift this mass up, right? And this point is known as pivot, right? So if we understand with what was lever, right? So the levers were used to pick up these heavier objects using this applied force, right? And obviously we're countering the effect of the weight of this object, right? Okay, so what is moment, right? Moment of a force, also known as turning effect of a force. I simply use the term torque, and this is the most recognized or universally acceptable term, torque, because in terms of science, this is a term that you will come across. These are the terms that only Cambridge is using, and this is more in focus by Cambridge. Usually by all others, if you go for American examination or IB, you will get to see this term torque. Why? Because we do understand that when we assess engine power, we discuss torque, that this generates this much Newton meters of torque, right? So what is moment of a force? Let's just say we have an object, right? We have a mass. We apply a force on this, and we do understand it will move in this direction, right? So if this is the applied force, then the motion is going to be on a straight line. Let's say this was on a horizontal surface. So this is a linear effect of the force, right? The force is able to only generate a linear motion. Let's just say if I just apply force upward, I try to lift it, then the object will also move in a linear fashion. But that is for a free object. What if I take an object, let's say another box, right, a square mass, but I pivot this to one center, right? Let's say I mount this on a wall, and now this is actually fixed to the wall, right? So if I apply a force, there isn't going to be any motion in any direction. Why? Because this pivot over here, pivot, which is holding it down, is not going to let it move in a linear fashion. Why? Because it's now fixed. It is no more on a surface. Let's say this is a surface down here, right? So this cannot move anymore in a linear fashion on the application of a force. What if I take another force, right? I apply this force at this corner, this very corner of this. You would find that this object will start to spin, right? And this spinning effect is what we call as a turning effect of a force, right? So this is the turning effect of this force, right? So whenever a force is applied away from the pivot, it will try to turn the object. And what is a pivot? A point where the object can rotate, but it cannot move in a linear fashion. The example would be a tire, right? So a tire is actually bound by its axle, right? So what we have axle over here, the axle actually is the pivot for that wheel, right? So if we take the example of wheel, so we do know that the wheel is going to spin, right? It is going to spin around. Another example would be a fan, right? It is fixed from the top, right? And it spins, and it rotates, right? So that is also the axle, that is the point of the pivot, right? That is a pivoting point for the fan as well. So rotating objects, this will incorporate rotational motion, right, rather than linear motion. Now we haven't discussed types of motion, as Cambridge does not discuss that in the syllabi for IGCSE, but I'm going to discuss that as a miscellaneous topic, so you can review that later and see what types of motion are there and how to differentiate them and how to incorporate those in your explanations or in your diagrams, right? So let's continue with our torque. So in this case, this force created a rotational effect, right? Now this is what we call as moment of a force. Now another example would be of a spanner. Let's say we have a nut, right? And we use a spanner, right? Here's a nut. We use a spanner to unscrew this bolt, right? So here's the spanner, and obviously when we move the spanner, this nut is going to rotate, right? So when we apply force, downward force, it will rotate this spanner, and this spanner in turn will try to unlock this screw or tighten this screw, right, whatever dimension it is. Let's say this, since this is in the rightward direction, so the clockwise direction, so it will tighten the screw, and if we put it the other way around, then it will unscrew this bolt, which is the left will loosen up this nut over here, right? So in this case we understand that this is the rotational point. I'm going to put it across over here, and the point of application of force is all the way here, right? So I have this question for you. What if the spanner were longer? What would be the effect? And you would have understood if you have ever changed the tire of your car, that the longer the spanner, the easier it is to unscrew. If the spanner is shorter, then it is harder. You need to apply more force. That means then that the distance from the point of application of the force to the pivot, right? Here's the pivot, right? And here's the point of application of force, right? So the farther it is, the more the distance, the lesser the force that is required. So compared to this, F2 versus F1, if we're supposed to unscrew this bolt, F2 is going to require less force, right? And that shows that this relation, right, the moment, right, the moment is directly proportional to the distance, distance, oh, it erased everything, okay, distance from pivot. The greater it is, the greater the moment, that means lesser the force. And also moment is also directly proportional to applied force, right? The greater the force, obviously the more the turning effect, applied force. So from here we can say that the moment of a force is equal to force multiplied by the pivot distance, which is d, right? Let's call this as d, right? You can use L, you can use D, whichever way it is. It's just length. So its units are going to be, then the moment is going to have units in newtons, and for D we have meters, right? So the units are going to be Newton meters. So this is what moment is going to look like, right? So there is a symbol tau, which is used for this. It is not used by the Cambridge book or the syllabus, but this is a university, as I said, acceptable symbol for moment. You can write the moment word as a whole, and you can use this Greek symbol tau, which represents torque or moment. This is the formula for moment, right? So let's do a simple example. Let's say what is the moment at point A of a force which is applied at this distance. Let's say force is 10 newtons, right, and the distance is about 50 centimeters, right, from the moment. So what is going to be the clockwise moment, right? So this is going to be clockwise moment, right? So what is clockwise moment? So we can calculate clockwise moment. Sorry, just a minute. Too short writing, right? Okay, moment is going to be F into D, which is going to be 10 newtons into. Now here's the deal that the units are in meters, so we need to consider this 50 into this. So if D is equal to 50 centimeters, then it is equal to 0.5 of a meter. So we're going to use 0.5 meters over here. So that is going to be 5 Newton meters. So that's the moment in the clockwise direction, right? Okay, now that is just the moment in one direction. At times we have an object which has two forces applied on it. For example, let's take another box, right? It's a square object. In this case, again it is pivoted from the center, right? This is the pivot. I'm going to write this is the pivot. Okay, now we're applying one force at this corner, F1, and I apply another force, F2, at this point. Now F1 is equal to, let's say, 10 newtons, and F2 is equal to 15 newtons. So you need to understand in which direction of moment or rotation, right? Either both way. We can also say rotation over here because it is going to rotate, right? Since these are unequal forces. Now if we draw the distance from here to here and here to here, right? So the D is same, right? It's a square, so D is going to be the same. So in both cases, let's say if D is equal to 20 centimeters, right? Which is going to be 0.2 meters. So let's do this. So moment, now understand that this F1 is going to create a clockwise moment, and F2 is going to create an anti-clockwise or counterclockwise moment. So this is counterclockwise and this is going to be clockwise, right? So we can say the clockwise moment is equal to F1 into D, which is going to be 10 into 0.2, giving you 2 Newton meters of clockwise moment, and the counterclockwise moment is going to be F2 into D, that is going to be 15 into 0.2, which is just let me get my calculator. Okay, so 0.2 into 15 is going to be 3 Newton meters, right? So obviously now we say a net moment. Where is the net moment? That is going to be you can say bigger value minus smaller, or you can simply say whichever value is bigger. In this case your bigger value is actually this 3 Newton meters. So the net moment is going to be equal to 3 minus 2 is equal to 1 Newton meters, right? And that direction is going to be counterclockwise, right? So that's your net moment. So it will rotate, but it will rotate in the counterclockwise direction, right? And why so? Because that was greater. So at times we have to identify the sum of these values, right? Okay, we also at times get a question. I'm going to take another example. For example, we have another object like this, right? And I say no this. Okay, let's take another example. Okay, of a spanner, right? Okay, let's talk about spanners. That is going to be more appropriate for our case. Let's just say you have this spanner. Again, here's the pivot. You have the spanner around it, which is going to unlock this, right? And it's a short spanner that you're using, right? So let's just say I give you D, the length of the spanner from this pivoting point D is equal to 50 centimeters and centimeters, sorry, and the applied force is 20 newtons, right? So you're using 20 newtons with the spanner which has 50 centimeter of length to unlock this nut, right? Nut unlocked. So if this spanner used uh, 20 newtons to unlock this spanner, how much force would a spanner of 70 centimeters would require, right, to do the same job? Now in this case, first we need to do is to calculate, let's call this F1 and let's call this as D1. So we can find moment 1, that is going to be F1 into D1. Again, this is in centimeters, so we need to convert this. So that is going to be 20 into 0.5. That is going to be sorry, 10 centimeters, 10 newton meters, right? 20 into 0.5, we get 10. So that is 10 newton meters. Now remember, I'm just going to represent it as tau 1, right? Now remember, this tau or moment is to unlock this nut, right? That is going to be the same value even for a bigger spanner or a smaller spanner. We'll do a smaller one as well, right? This one is a bigger one. So in this case, we're going to keep the tau same, but we're going to equalize that to F2 into D2, and we're supposed to find F2, right? We're supposed to find that. We have this D2 over here, right? D2 is 0.7 meters. So that is going to be 10 newton meters equals F2 into 0.7 meters. Now meters can be cancelled out, so newton is going to be left, so it is going to be 10 divided by 0.7 is equal to F2, right? So once we do that, 10 divided by 0.7, so that is going to be equal to 14.285 newton meters, right? And to roll it out, 257, right? So we can just create into a more better one, that this is going to be 14.29 newton meters. I'm just going to round off. That is force 2, right? So as you can see, when the spanner got longer, then less force is required to unlock the same bolt. Remember that the moment will be same to unlock this nut, right? Because the nut is not changing, it's the spanner that is just changed, right? And that's the length of the spanner that has changed, resulting in lesser force required to unlock that. What if spanner was of 30 centimeters, right? What about that? Okay, let's do that again. So tau is now going to be F3 into D3, where D3 is now this 0.3 meters, right? This one. So in that case, the moment is going to be the same. Sorry, I need to write the value. Okay, that is going to be the same, which is 10 newton meters that we calculated for the nut, right? And F3 is what we need to find. So F3 is unknown into 0.3 meters. Again, meters is cancelled out, so it's just newton left. So it's going to be 10 divided by 0.3 is equal to F3, right? So again, we simply do this, 10 divided by 0.3, that is going to be 33.33 newtons of force, right? So understand this. Oh, sorry, I did the mistake over here. It's not newton meters, just newtons, right? Okay, there we go. So as we can see, F3 is the greatest of them all. Why? Because to unlock the same bolt, if we use a smaller spanner, it would require more force. If we use a longer spanner, we would require lesser force, while the original spanner was only requiring 20 newtons of force to unlock this. So that's the effect of the length on the moment for a fixed object, right? Also, the increase in force will also result in more torque, more moment being generated, but in this case we did not require the change in moment, because we were discussing the same object, which was this nut over here, right? So if the nut is the same, or the object is the same, then it is going to be fine. We also need to understand what is pivot, right? So I'm just going to draw an example of a signboard, right? So it's a very big signboard that has a base like this, right? Now obviously there's no weight over here, right? Nothing over here, so the moment is going to be clockwise because of this extra mass over here. But understand that this point over here is going to be the pivot from where it is going to topple. So the point where it is going to topple is actually the pivoting point, and we need to understand the center of mass of this object to understand where how far it is from the pivot. So this is going to be our D, right? Now we will understand what center of mass is and center of gravity is in a moment, but for now understand that this is the pivoting point. And also let's say to balance this, I put a little brick over here, so that brick again from its center is going to have this much distance d2 from the pivoting point, right? So this W1 versus this W2 weight, right? So if they are balanced, then definitely W2 into D2 should be equal to W1 into D1. Here W is the force, right? Weight is also a force. We discussed that in the force unit, that this is another name for force, right? It's due to the mass. So they should equalize. That is how you're supposed to solve this. Also remember that it is always the center of mass or the point of application of the force. In this case, we're not applying an original mechanical force, so it is just due to the weight that the force is there. So that is to be from the center of mass, right? Center of mass. So that is from where the weight is going to be applied. So you need to calculate the distance from pivot to center of mass. That is going to be your line of application of force. Even in this case, it is going to be from the center of the mass, so that is going to be D2. And since D2 is longer, so we need very little weight on this side, and since D1 over here is smaller, so we can manage a larger weight by balancing it with a smaller object on this side. So this is a very important case, and it's a very troublesome case for some of the kids. It's from the past papers. Several times such cases have appeared in questions. So just do go through those questions and let me know if you have any troubles regarding this. So remember this, that these are the points that you need to understand while discussing this, right? So over here I'm going to conclude this tiny little topic and move on to something which is, I think, is a miscellaneous topic for me. I consider as the point of application of the force. So what is point of application of the force? Let's say you have this object which is free to move, right? It is lying on a horizontal floor. Now you have one force which is applied over here, right? This is the center of mass. And what is the center of the mass? It is actually the cross of these diagonals, right? I'm trying to draw these dotted lines. Okay, this is the center of mass, right, where the most of the mass is concentrated for this object, right, from all corners. Okay, another force is applied at this point. Now which force is going to turn it over, F2 or F1, right? And which force is going to create a linear motion? So over here F1 will cause linear motion, right? And in this case F2 will cause rotation, and that is what we call as moment, right? The rotational effect of a force. Now why is that? Because that's the application point of application of the force. So let me just draw a dotted line representing the center, right? If the forces are applied on the line of action, right, Where's the line of action of the force? The line across which the force is going to be applied. If the line of the action, right, line of action, right, in this case these dotted lines represent line of action. If the forces are applied on the line of action, in the direction of line of action, then it will have a linear motion, and if they are not, that would cause some sort of rotation in the object, right? So this is one sheer example of what line of action is. Now at times you've got forces which are not in the line of action. For example, we have another square box. Please don't mind the shape of the box, I'm just trying to be quick. One force is applied here, another force is applied here. Now that's the center of mass, right? This is the center line of application at which the object is supposed to have linear motion. So this is F1, this is F2, and F1 is equal to F2. Do you think the object is going to rotate? No, it is not going to rotate, because the clockwise and the anti-clockwise rotations are going to cancel out each other, because the distance is the same from the center, that is going to be this d, right? That is same for both, and since the forces are equal, then the counterclockwise moment is equal to clockwise moment, right? So they will cancel out each other, so again we will have no rotation, right? So this understanding of line of action is very important when for example another object is here, right? That's the line of action. I'm just going to draw this. If one force is applied in this direction, this is F1, and this is F2, right? Also over here F1 is equal to F2, then again no motion. Why? Because these forces will cancel out the effect of each other. Now these are two conditions of equilibrium. Over here I will discuss what equilibrium is, right? And equilibrium is a state in which an object tries to retain its rest or uniform motion, right? And that is uniform motion, right? That in this case is going to be condition 1. Now there are two conditions for this, right? First condition is when sum of all forces is equal to 0, which is this case over here, right? Since both forces cancel out each other, so there's no linear motion, the object will stay in its position of rest, or let's say if it's in a uniform motion like Earth, it will remain in uniform motion. Its motion will not get disturbed. Why? Because the forces are cancelled out. For example, the vertical force, if we take F3 and we take another F4, and we say that F3 is equal to F4. If these are not equalized, if these are not cancelled out and the sum is not 0, then we are going to have motion, right? Now there is second condition of motion, and that refers to sum of all moments is equal to 0, which is this case right over here, that the sum of both clockwise and anti-clockwise were equal to 0. They cancel out each other, so there was no rotation. So these are the two conditions of equilibrium, which you need to understand, that the sum of all forces must be 0 and sum of all moments must be 0, right? So this is when an object is truly in equilibrium, right? That's when we say that the object is truly in equilibrium. Otherwise, if either of these two conditions are not met, then we cannot say that the object was truly in equilibrium. There must be some sort of motion associated, or acceleration associated with the object, right? So that's the understanding of line of action, that that the forces, if they are there in the same direction but on different points, they may cause different moments, if the both forces, let's say if I apply another third force over here along with it, so they are parallel to one another, but they are in the same line of action, so they will cause they will cause a double rotation, right? So do understand, do remember this two conditions of equilibrium. That's a very important fact. uh, Now, moving on to our third topic, which is the center of mass and center of gravity. So, what is the center of mass? It is the point where all of the mass is concentrated. For example, for a sphere, it is the center. For a square, it is again the cross section of its diagonals. For a rectangle, it is again going to be the intersection of the crossing of these 2 points. For a triangle, right, that is to be going to be the side diagonals, which we take from one corner to the other. In mathematics we do that, so that is going to be the pivoting point. But what about an irregular object, right? Now that is very hard to do. So what we do in this case, that we take this object, right, let's say this is the object. I'm just going to draw this irregular shape like this, right? So for the ease of uh, understanding, because I won't be able to draw this as identically as much as I can do this, right? So this is much more easy to understand. Okay, for this I'm just going to pin it out from this point, right, P1. So once I pin it to wall, we would find that this object will tend to hang somewhat like this, right, from this. And what we do, we take a plumb line and we just hang the plumb line like this, right? We'll understand what a plumb line is. Plumb line is used by laborers or the construction engineers to see whether the walls are well straight. So this plumb line will let us know. We simply just track the plumb line and we draw or trace the line on that object, right? That is point 1. Now we take any other point. Let's say we take this point, right? So now I hang this from another point and it is going to hang something like this, right? As I said, I won't be able to get as much identical. Now this yeah, here was P1, P1 was here, right? So this is where the P1 crossed. So I'm just going to hang it. Okay, it is not going to hang like this that easily. Let me just redraw this. Okay, all right. So if I hang it from here, it is probably going to hang something like this again. But now remember the first trace that we did, which was this point going like this, right? Now this is going to be hanged from here. So once I do this, I'm going to trace another line, and wherever these two hanging lines will intersect, that is going to be your center of mass, where the mass of the object is concentrated. So any irregular object, similar way in this case, let's just say if one line crossed like this, then the other line crossed like this, so that is going to be the center of mass, right? Or we can take a third line which will go again from the same point, so that's the center of mass, right? So you can do this by easily doing this. We can take diameters for the case of circle, right? But irregular shapes are much harder. So how do we do that? We simply pin it from any point of your choice and let it hang. Use a plumb line to trace that line over here, and then we just take two of these lines, and wherever they cross, that's the center of mass, right? So center of mass is where most of the mass of the object is associated. Let's say if we discuss the case of a car, now I'm just going to draw a rough car over here. Now we do understand that on top there is a windshield and there are a lot of empty spaces, and there is the engine over here, the lights and the tires and everything. So most of the weight of the car is going to be here, somewhere here. Why? Because this is more empty space and more populated, right? Why more populated? Why? Because you know uh, we have the engine here, we have the wheel, the assemblies, all the components of the car which are lower than this top. So the center of mass is right here, right? And this center of mass will identify whether this object is going to be stable or not. Now remember, having a lower center of mass is much more easier. It is much more better in terms of stability. For example, I have a book. Now here's the center of mass, which is very closer to the surface, right? Let me just redraw this case. Let's say in these two cases, we're going to understand the stability. Now what is stability, right? Stability, now if the center of mass is closer to the surface, right, this is a COM, compared to the another book which I stand vertically, right? It's standing vertically. Now again, the center of mass is going to be the cross section of these 2 points, right? I'm just going to draw these dotted lines over here. Now this is also the center of mass, right? Center of mass. Now in this case, as you can see, the center of mass, this D is more than this D over here. So which one is more stable? This one is more stable. Why? Because there is very little chance that this will topple. Why? Because the center of mass is much closer to the surface. In this case, even a little force will topple this down. Why? Because the center of mass was farther away, and every object tries to have a lower center of mass, whether by toppling or whether by application of the force. So to attain stability, it will reduce its height of center of mass, right? So over here we will understand some states of equilibrium. Now do not confuse this with conditions of equilibrium, right? Now there are 3 states of equilibrium. Number 1 is stable, right? And we discussed what is stable. When COM is closer to horizontal surface, right? Whenever an object has a center of mass which is closer to this to a horizontal surface, it won't tend to topple, right? If I apply force on this book, then it is going to move linearly, but it won't topple anywhere, right? Number 2 is unstable, right? The example again I'm going to give of a book, right, which is standing. This is the COM, right? When the center of mass is farther from horizontal, right, surface, which is again the case of a standing book, that is going to fall easily on the application of force, right? If the force is applied, it will topple. In this case, if I apply force, it would just move in a linear fashion. This one is having rotation, right? And the third one is a very unique case which we call as neutral state of equilibrium, when COM does not change when force is applied, or it is tried to be disturbed, right? And that is the case of a sphere, right? And many other cases are also there. Why? Because if I apply force on a ball, it will just rotate and it will move forward. It will have rotation, tau, it will also have velocity, but the COM is not going to change until unless it bounces off, and even then after bouncing it will come back to a neutral state. So the COM will not change over time. It will elapse the same height even if the object moves back and forth, right? So that is a neutral state, which is the most unique state, right, of equilibrium. Now understand, these are, again I'm saying, these are states of equilibrium. I'm just encircling this for your understanding, and not to be confused with you know, the you can say sorry, okay, this is not to be confused with over here what we had, conditions of equilibrium, right? These are conditions, right? So do not confuse these conditions with these stability based states, right? These states only define the stability of an object. right? Now over here I'm going to add a unique topic. uh, I still need to discuss the center of gravity first before we get into comparing these ideas. Okay, for this, what is center of gravity? Let's say if the object, you have an object like this, right? It's a rectangular object which is hanging from point A, right? Which is the pivot as well, right? And obviously, I'm just going to draw these pink lines, diagonals. So this pink point B is center of mass, right? Where do you think is the weight of the object being applied? Why? You need to understand that the weight is acting at the bottom of this, right? Weight is the center of gravity, is the point where the weight of the object is applied. So COG is the point where the weight is acting, right? And in this case, it's acting at this bottom point because that's from where it wants to fall, but it's stopped by this pivot. The center of mass is not in play. Understand this, that the object will always rotate if the center of mass and center of gravity are not in the same line. Although I tried to draw them to be in the same vector line, same line of action. Again, if the line of action, if any force is there which is not across the line of action, we understand it will create a rotation. For example, we have an object which is like this, right? It's somehow we just elevated this. This is the pivot, right? This is the COM, and we understand that in most of the cases the center of mass is also the center of gravity. Why? Because the weight is going to act from where the majority of the mass is going to be, and definitely gravity is going to act right there. But in this case, the center of gravity is going to act like this. It will cause rotation, right? So if uh, the center of mass is away from the horizontal surface, it will try to cause some sort of rotation, right? So that's a brief idea of what center of gravity is. It is most of the time the center of mass as well, right? And we simply use that to understand the rotations of these objects. In this case, the example that I gave you over here for this this board, right? This is really important, right? So just do go through this question, and you will have a better idea of how these things work. I hope I was able to clarify some of the basic concepts of these topics, and I wanted to give a brief idea of a miscellaneous topic, but I actually covered it while doing these line of action and center of mass. So that was the miscellaneous topic that I was going to discuss, the states of equilibrium as well as the conditions of equilibrium that I've covered over here. The only thing that is left over here is the odd question. Now for the bonus, I'm just going to create a practice question. I'm just going to keep it an untitled page for the moment. Okay, let's just say you have a series of stands, right? And these are rotating stands. Now if you can pull this off, it's a very fun question to deal with. I usually give this as an example in my classrooms. It's not in any book, it's my own made question. Now over here you have a mass which is hanging, right? It's a mass that is hanging, and here there is another bar at the bottom of it that is supposed to lift it up. Now the other end of the bar is very long, right? I'm just going to give you distances. This is 5 centimeters. This is going to be 8 centimeters. This is actually 4 centimeters, and also this is also 4 centimeters for the pivot. Over here we have a small little rotating bar, right? Just God, this is too bad. Okay, yeah, there we go. We have a small little, and that is just 2 centimeters, right, on each side. Now I want to lift this up. Definitely I need to push this push this up, right? I need to push this up so that it rotates up. When it will rotate up, it will push this bar down, and that will lift this object up, right? So this is like gears which come into contact with one another. If this gear rotates here, then it is going to rotate this gear the other way around, and then when this gear rotates the other way around, this goes here, right? So this is how the rotation of the gears work. So they can pull onto each other. This is the same way gear ratios are also decided for several things. Now calculate the applied force if mass is equal to 250 grams. And how we can do this? First, give it a try. I'm going to put in the solution right here. I'm just going to discuss the solution. So first of all, I'm just going to calculate the weight, which is the force. So weight is going to be mass into gravity. I'm just going to move down a little bit. So that is going to be weight is equal to 250 grams. So mass is 250 grams, which is going to be 0.25 kilogram. Again, we need to be in the SI units. So it is going to be 0.25 into 9.8. That is going to be the weight, right? Just let me calculate this on my calculator. It is going to be 0.25 into 9.8. That is 2.45 newtons. That's the force which is there. Now let's call this tau 1 for this one. Let's call this tau 2, because since these distances are equal, so this tau 1 is going to be the same for both sides, right? It is going to be the same for lifting this mass. We need to have the same torque which is being exerted by this mass, but this is 5 centimeters, this is 2, so I'm going to use different of these taus, and then I will call this as tau 4. Again, over here the distances are same, so it is going to be same torque on both sides. Remember, unless the force or the distance changing, the torque is supposed to be the same, and we will keep the torque same eventually. So I'm just going to calculate the moment of this weight. That is going to be weight into d. Again, tau 1 is going to be sorry, it's oh, there you go. Okay, that is 2.45 multiplied by 4 centimeters. Again, we need to convert that. That is going to be 0.04 meters, and let me just calculate this. So 2.45 into 0.04, that gives me a value of 0.098 Newton meters. That's the torque generated by you can say the clockwise the counterclockwise moment generated by this mass, right? And that is going to be the same amount of moment I need to apply on this end over here, right? So that it is lifted up, right? Okay, sorry, I just made one mistake, technical mistake. I hope you are able to understand what I just did, right? This is supposed to be like this, and this is supposed to be on the higher end, so that this pulls it down. Now that's better, because yes, this needs to go down so that it lifts this one up. It will push it down, so this will go down and this will move up, right? So to counter this counterclockwise torque, we need to have a clockwise torque, which is going to be generated by this bar of 5 centimeters. So we're going to now go with that. For tau 1 being equal to tau 2, we need to have an understanding that how much force is required on this end. Now I'm just going to go with this, that this is going to be 0.098 equals to F. Now we're just going to keep this F as is, right? Which we're not going to discuss this. That is going to be into 0.05 meters, right? That is the force required on this tau 2, right? And that is going to be, again, F is going to be, let's call this F2, right? So which is going to counter this weight over here, but that is not it. We're supposed to apply the force at the third segment, not in the second one. So that is going to be 0.098 divided by 0.05. It is going to be 1.996 newtons. Now that is for this end. Remember, that is supposed to equalize for this as well, right? So we need to understand that the torque is again going to be the same for this bar, so we're just going to equalize this, that the force is again going to be equal and the torque is going to be 0.098, right? But for a longer one, that is going to be the torque generated by this is going to be F3 into 0.08, and F3 that is going to be generated is going to be 1.225 newtons, right? Now that is the force 3 which is being generated by this. Again, we're supposed to calculate this force, right? And over here we need to work out the third one, the fourth one. So the fourth force is going to be the same as 0.098, which is the initial torque, divided by 0.02 meters. That is going to be the highest value, right? And that is going to be that is going to be 4.9 newtons, and that is the sum of the force that we need to apply on this to get this thing that is going to lift this weight. We need to apply 4.9 newtons of force on this end, so that it delivers that much force to this point. It will lift this up, this one down, this will push it up, and then this will going to lift it up. So nonetheless, this is one troubling case. This kind of a question is a very rare question to find. Usually it's a 2-point combination. I make it more complex by adding the third pivot, but remember, the torque is going to be the same across all these bars, so it's very little force that is going to change. We can actually calculate different torques on each of these, that how much torque is going to be there from each side, and the force is going to be manipulated across these bars. It's a fun case. It's a very troubling case. As I said, it's not a very common question. Usually it is a much easier version of this question that is being asked. So hopefully I'm able to help you understand what torque is, and how you can work out some of these examples of torque, and how you can do this. Another more common example is actually of a crane, right? That's a more common question, that a crane has these balancing blocks over here, which is a steady mass, and it is going to lift something up, which is M2. So if M2 is certain value, let's say it is X, how much M1 is going to be required, considering that this is 5 meters and this is 20 meters away, right? So this obviously needs to have a lot of mass at this end, because the pivoting value of this is going to be the pivot, right? So the pivot is here. So this is also a similar case than this, but much more easier to do this. Simply you simply equate this as M1G into 5 should be equal to M2G into 20 meters, right? Now that is how you can solve this. I hope I'm able to clarify some of the basic concepts of torque. If you have any issues or any queries, just leave me in the comments, and I'll try to respond as soon as possible. Thank you.